Calculus without derivatives is like cooking without fire. So said Ralph P. Boas, a mathematics educator. It is so apt because derivative is rate of change, and rate of change is all that computational calculus is: differentiation, integration, and differential equations. To be particular, it is the limiting value of the rate of change at a point or instant of a function. This we know from the previous lessons. There is actually little more than this. Let us see what else there is. Calculus is all focused on making more sense of the reality of continuous change. In general, calculus is all about how continuous change of a quantity may have meaning beyond the change being witnessed in that quantity. It is how a change in a quantity can reflect change in another. For instance, distance traveled with respect to time throws new light on the nature of motion, by way of a new quantity we call speed of the motion. How the change in the volume of a sphere due to a change in its radius gives us insights into the changing capacity of the sphere as its size increases. Or how change in acceleration of a body in motion over time affects the lack of comfort in motion by way of what we call jerks in motion. Calculus empowers us with analytical wares like derivatives and integrals to precisely identify, quantify, and analyze rates of change. Derivatives is the measure of instantaneous rates of change, the nature of change that best characterizes continuous changes. To be sure, a rate of change could be the average rate of change too, but it is the instant rate that best characterizes continuous change, the real world. And to be right, the instant rates are also average rate, but when the instant or any other variable quantity is near zero. To be true, having explored limit and continuity, the only substantive learning on derivatives is the realization that derivative problems are ultimately the good old algebraic manipulation and trigonometric functions. While we will witness this in a later lesson, we next revisit the key learning on derivatives from the previous 3 lessons on faces of derivatives and those on limit and continuity. The 3 lessons on the faces of derivatives were meant to bring home the following aspects of derivatives. First, derivatives are mathematical creation, yet they matter physically. Second, derivatives are creative creations. We find meaning in the rate of change of something. Third, derivatives are need-driven. We find the changing relationship of things to know better. For example, attenuation derivative in earthquakes that measures the changing velocity of tremor over distance on the crust. Fourth, derivatives are needed for precision. Recall how the derivative of the rate law is not enough for precise control of chemical reactions. Fifth, derivatives may just the thing to know about change. For example, the instantaneous rainfall or the instantaneous speed of a car at a sharp curve matter way beyond we can imagine. On the whole, derivatives are very real quantities derived wholly mathematically. Let us briefly touch upon what we know about derivatives from the lessons on motion and the 3 challenges of computing the instantaneous rate of change. First, there are many quantities that are physically non-measurable, not physically ascribable, in the sense of measurability in a snapshot at an instant, or not the way we can observe and measure time lapsed, distance traveled, mass, etc. And these non-measurable quantities potentially have meaning. Second, many of those physically non-measurable quantities in the real world of continuous change are the measure of change of something which can be directly measured as above. Expectedly, there is little static, physical about these non-measurable quantities. For example, the measure of change of distance over time is an interesting new quantity about motion, speed. And there is nothing static about speed. It is created in motion. Third, there are also many quantities that are the measure of change of something that is in itself not directly measurable and is a measure of change. Acceleration is the rate. Let us now move on to what we can refine and add to the previous learning on derivatives. A derivative is a rate of change of the primary function, and this rate of change of the primary function becomes the instant value of the derived function at a specific point when or where the rate of change is computed. The process of finding derivatives of a function is called differentiation or derivation. That is, the output of the process of differentiation is the derivative. Differentiation numericalizes how much has the dependent variable changed, with an infinitesimal change in the independent variable. To mathematically express a current in a conductor, we create a function that quantifies the flow of electric charges in a conductor in a given duration of time. The process of differentiation helps us to find the rate of change in the flow of electric charges through a cross-section of the conductor at any given instant of time. Differentiation numericalizes how much the dependent variable, the amount of electric charge, changed with an infinitesimal change in the independent variable, time. If I is the electric current, Q is the electric charge, and d by dt is the change in the electric charge function over a very small change in time, then mathematically, I equal to dq by dt. Graphing is possible for every function. The relationship among varying quantities is best captured graphically by curves that show continuously changing slope. The slope of a line or a curve of a graph of a function describes the rate of change of the function. That is how rapidly the outcome of a function changes with a unit change in its inputs at various points in its domain, and tells about the steepness and direction of the lines and curves. For a straight line, the rate of change remains constant or uniform. For a curve, the rate of change keeps changing or is not uniform. The two graphs show the changing slope and the rate of change of the functions that are graphed. How do we calculate the rate of change? Mathematically, not through the slope of the tangent. Rate of change is the ratio of the change in value of the function x, that is y or fx, due to a corresponding change in the value of x. Mathematically, where x0, y0, and x1, y1 are coordinates of the pre-change and post-change conditions of the two quantities in the relationship expressed by a function. In terms of the values of the function fx, the rate of change can be defined for the function as shown in the formula. The rate of change is rarely constant in the real world, that is. The relationship of quantities is not really linear for most situations. To find rate of change or slope around the point x0, we take x1 very close to it. To find slope, we need 2 points. x1 can be taken as x0 plus h, where h is a very small quantity. It is infinitesimal quantity approaching 0. Solving mathematically. On the graph, the derivative of fx at any point x0 is given by the formula below. Here h is an infinitesimal quantity, tends towards 0. Derivative can be expressed in general for no specified point as the flowing formula, where delta x stands for infinitesimal change in x. Since dx is a small change along x-axis, this quantity can also be taken as h, and thus can be written as the following. To denote the instantaneous rate of change or derivatives in a simplified mathematical way, we use the derivative notation. df by dx or dy by dx or f-x. It is the same as the ordinary rate of change, delta y by delta x, except that both the changes delta y and delta x are extremely small. Limits and continuity and derivative. A function must be continuous at a point for the derivative to exist at that point. This is because the derivative involves taking a limit, and for the limit to exist, the function must be well behaved near the point. That is, limit must exist at that point. The properties of limits also play a role in finding derivatives. However, the converse is not necessarily true. a function can be continuous at a point without being differentiable at that point. For instance, there may be a sharp change of slope just around that point. Recall, graphically, the derivative at a point represents the slope of the tangent line to the graph of the function at the point. Derivative measures how the function changes around that point. For example, the absolute value function f(x) equal to modulus x is continuous at x equal to 0, because the modulus of minus x and positive x around 0 is the same positive quantity. But the function is not differentiable at x equal to 0, because the derivative from the left and the right do not match. The left is -1 and the right is +1. To some, while continuity at a point is a necessary condition for differentiability at the point, it is not a sufficient condition. Thus, a function being continuous at a point does not guarantee the existence of a derivative at that point. Fundamental relationship of differentiation and integration. Derivatives and integrals are essentially inverse operations of each other. If derivative is about instant change values, then integration is about the effect of the instant changes over a period, given the rates of change over the period. We will next see how the instant rates accumulate through the idea of average rate. For example, acceleration is instant rate of change of velocity, a derivative of velocity, but the integration of acceleration is average velocity over a period. Integration of acceleration over a period will give the total change in velocity in that period, and by default, the average velocity over the period. Instantaneous rate, average rate, and integration. The instantaneous rate of change at any time in a period, the average rate of change in that period, and the integration operation over the period bear an interesting relationship. The average rate of change over an interval a to b is closely related to integration over that interval. For instance, if f(x) represents a velocity function, then integrating f(x) over a to b is the total distance traveled from during a to b by kind of multiplying the average velocity during a to b with the duration between a to b. On the other hand, the derivative, or the instantaneous rate of change at a specific point, is used in integration to get the total effect of change over a period by way of accumulating or summing up the effects of that rate of change over the period. Thus, the average rate of change over an interval and instantaneous rates in that period are conceptually related, but the two are distinct concepts in calculus with different interpretations and applications. Derivative of a function is the way we measure the basic nature of any continuous change, its rate of change. The function itself represents the changing real situation. Limit is that idea that makes the rate of change instantaneous. Limit helps us ensure that the computed rate of change at the point or instant of interest is indeed unchanging and representative of the rate of change at that point. That is the continuity idea about derivatives. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.